Hello everyone, and welcome to this lesson on covalent adaptable networks, or CANs for short. These materials are a fascinating class of polymers that combine the best of two worlds, the recyclability and reprocessability of thermoplastics with the mechanical strength and chemical stability of thermosets. As we know, thermoplastics, like polyesters for example, can be reprocessed in the molten state and remolded virtually endlessly, but they often lack the strength and stability of thermosets. On the other hand, traditional thermosets like epoxy resins, for example, are highly durable and chemically resistant materials, but they cannot be reshaped or recycled once cured. Covalent adaptable networks bridge this gap. They are cross-linked polymers, just like thermosets, but they have a very unique feature. Their covalent bonds can break and reform under certain conditions. This means they can be reshaped, repaired, and even recycled without losing their structural integrity. In this lesson, we will explore the chemistry behind CANs, their unique properties, and the role they can play to make composite industry more circular. Let's dive in. At the heart of CANs are dynamic covalent bonds. These bonds can reversibly break and reform under specific stimuli such as heat, light, or chemical triggers like pH changes, for example. This dynamic behavior allows CANs to adapt their structure without losing their overall mechanical stability. There are two main types of CANs, associative and dissociative networks, which differ in the bond exchange mechanisms. In associative CANs like Vitremes, bond exchange occurs through a transition state where all bonds reform as new ones break, maintaining network integrity during reprocessing. This process is often thermally driven and allows for continuous reshaping without losing material properties. In contrast, dissociative CANs involve complete bond breaking before new bonds are formed, leading to a temporary loss of network structure. This makes dissociative CANs easier to reprocess or recycle, but can reduce their thermal stability. Overall, associative CANs are typically more robust, while dissociative CANs offer greater flexibility in reprocessing and recycling conditions. To form a covalent adaptable network, different dynamic chemistry approaches can be used, relying upon different covalent bonds. Some of the most common ones include the Disolder reaction in dissociative CANs, and disulfide exchange, transesterification, and imine metathesis in associative CANs. However, many more options and pathways exist, each featuring specific characteristics and advantages, as will be discussed in more detail in the following lessons. But what are the key properties that make CAN systems so interesting? First of all, CANs exhibit reprocessability. Unlike traditional thermosets, which are permanently shaped after curing, CANs can be reshaped and remolded multiple times without significant degradation. In addition, the reversible nature of the dynamic bonds allows CANs to be broken down and reused, enabling effective recyclability. CANs also have the self-healing capability. If the material gets damaged, applying heat or another external stimulus can trigger bond rearrangement and restoration, yielding effective damage repair. The same approach can be exploited to induce autonomous welding without the need of adhesives. To achieve this multifaceted behavior, CANs can be tailored to respond to specific triggers, such as temperature, light, or even chemical stimuli. Combined with their mechanical strength, durability, and thermal stability, these characteristics make CANs very appealing for a number of applications and market sectors. In particular, covalent adaptable networks can be a game changer in the composite field by enabling recyclability and repairability. As we know, traditional composites, like carbon fiber reinforced composites or glass fiber reinforced composites, are hard to recycle due to the thermoset nature of their polymeric matrix. CANs instead, thanks to the presence of dynamic covalent bonds, allow the matrix to be reshaped, repaired, or recycled without damaging the fibers. This extends the lifespan of the material, reducing waste and aligning with the principles of the circular economy. By facilitating reuse and reducing the need for virgin materials, CANs may enhance the sustainability of composites, making them ideal for industries like aerospace, automotive, and wind energy, where lightweight, durable, and eco-friendly materials are needed without compromising on performance. Of course, CANs aren't without their own challenges. One major issue is the kinetic control of the reversibility. The dynamic bonds in CANs need to be stable under certain conditions, but swiftly responsive when needed. Achieving this balance can be tricky. Another challenge is their scalability. While cans show great promise in the lab, producing them on an industrial scale remains a hurdle. Finally, the issue of cost. Many of the dynamic chemistry used in cans require expensive catalysts or reagents, which can limit their commercial viability. But the future is bright. Research in this field is constantly progressing towards new dynamic chemistries for even greater control of the bond exchange dynamics. Advances in green chemistry are also helping to reduce costs and environmental impact. To wrap up, covalent adaptable networks are an exciting class of polymeric materials that combine the durability of thermosets with the recyclability of thermoplastics. Their dynamic covalent bonds enable unique properties like reprocessability, self-healing, and stimuli responsiveness, making them ideal for a wide range of applications. While challenges remain, the potential of cans to transform industries and promote circularity is undeniable. In the next lessons, we will discuss in more detail the most important classes of associative and dissociative cans, and on how to assess their response. The major focus will be on their use as matrices for fiber-reinforced composites, and on their role in making the future of these materials more circular and sustainable. Thanks for watching.